Okay, folks, let's wrap it up today by talking about gluconeogenesis. So, after we've kind of blown through our glycogen stores, our body has to switch to synthesizing from scratch glucose through gluconeogenesis. So, this is providing our bodies most of the glucose during fasting conditions. And we're synthesizing this glucose from a wide variety of non carbohydrate metabolites, such as lactate, pyruvate, TCA intermediates, carbon skeletons of most amino acids. It is amazing how our bodies can take kind of all of these different types of small molecules and eventually get them to glucose for our bodies to stay alive. However, these processes, as we're going to see, do require a little bit of an input of energy. So oftentimes, gluconeogenesis is powered by fatty acid breakdown. This makes sense, right? If we're in fasting conditions, our bodies turn to burn fat, right? And we'll see very soon how much energy is produced through lipid breakdown. So, big picture at first, folks, gluconeogenesis is mostly the reverse of glycolysis. The first thing that we have to do in gluconeogenesis is convert those starting metabolites to oxaloacetate. You can see here down at the bottom that, for example, if we're starting with pyruvate, we convert it to oxaloacetate before we get to PEP. This is kind of cool, and we'll see that happening. You'll notice, though, it took one step to go from PEP to pyruvate, and it's taking two to go from pyruvate back to PEP. We have to keep in mind that because the forward reactions are rate determining, they cannot be reversed. So we need a new mechanism to perform the chemistry to get us back from pyruvate to PEP. And that is the first step in gluconeogenesis. Then, as we move back through glycolysis in the direction of gluconeogenesis, all of these equilibrium steps are easily reversed, right? And then also our other two rate determining steps performed by hexokinase and phosphofructokinase need substrate cycles, so enter fructose bisphosphatase and glucose 6 phosphatase. We're not going to look into those mechanisms at all because they are less fun. They are really just hydrolysis reactions that we have seen plenty of times at this point. So we'll focus in on the first rate determining step of gluconeogenesis, understanding that the rest of the pathway is mostly just done in reverse, swapping out the other two rate determining steps for hydrolysis reactions. So if we're going to make oxaloacetate from pyruvate, we need to add carbon dioxide. How does that happen? Carbon dioxide, as we've mentioned briefly in this class, doesn't really just float around in our bodies as is. It's oftentimes immediately converted to bicarbonate, bicarbonic anhydrase. So we have this enzyme, pyruvate carboxylase, that helps us attach the CO2 using a cofactor biotin. Let's watch. So this mechanism is going to start by the cleavage of ATP. There's our input of energy, hydrolysis of ATP, making the process exergonic, releasing energy. We have a decent nucleophile, this negatively charged oxygen, attacking our favorite electrophile, the thing that looks like a carbonyl carbon, breaking that bond and shifting that phosphate onto carboxyphosphate. From there, we resonate the lone pair on the negatively charged oxygen of CO2 back in, breaking the bond with phosphate, leaving us with just CO2. CO2 is a fantastic leaving group. Now in comes biotin. Now biotin has this lone pair on the nitrogen that can do a nucleophilic attack and trap that CO2 and hold onto it until we need it. Then, once we've kind of attached, where's my mouse? Once we've attached that CO2, it is time for us to be able to use that CO2 to plop it onto pyruvate. So in comes pyruvate. to get the CO2 onto pyruvate, we first need biotin to release the CO2. Easy enough. Just do all those resonance steps again. Resonate that back in. Bam, bam. CO2 can kind of reversibly bind biotin, right? It can pop on and pop off quite easily. Once it pops off, we have a few things to do before we can attach that CO2 to pyruvate. We first need to do a little bit of acid base. So biotin, in addition to doing this one carbon transfer, one carbon because there's one carbon in CO2, does this acid base step where it again takes that same lone pair that did the nucleophilic attack and it deprotonates our pyruvate, giving us this enolate kind of structure here, which we know then can behave as a nucleophile. If we resonate that oxygen, the lone pair and the oxygen back down, and that carbon can do the nucleophilic attack on the thing again that looks like a carbonyl carbon, giving us at the end oxaloacetate. So we're halfway back to PEP. The second step in this reversed pathway is done by PEP carboxykinase. Oftentimes you'll hear it called PEP-CK. So we need to now decarboxylate oxaloacetate to make PEP. But again, this needs to be exergonic. So we pull in another high energy molecule, GTP. Remember, folks, CO2 is a fantastic leaving group, so we can just resonate that lone pair in and CO2 can leave. Of course, carbon only makes 4 bonds. So when we resonate that lone pair in after CO2 leaves, what we're going to have happen is attack of this lone pair from this oxygen that was in that carbonyl to, again, a great electrophile, the phosphate. Now this cleavage of the GTP again provides us that energy and phosphorylates part of the oxaloacetate to then form PEP, our high energy molecule that's going to be then shuttled backwards through gluconeogenesis. Now recall, folks, that if we're starting with pyruvate to then make oxaloacetate to turn to PEP, that pyruvate was in the mitochondria because it's being used in the citric acid cycle. So how do we get that PEP back to the cytosol where gluconeogenesis needs to happen? We have ways to take care of that. So in humans, the oxaloacetate converted to PEP can be shuttled directly into the cytosol, right? We can just take that PEP, bam, shove it into the cytosol for gluconeogenesis. If you plan to take the MCAT, you may also need to know about the malate aspartate shuttle that is on the slide here. I am not going to talk through it. That's a bit more complicated, but it again is a way for us to eventually get PEP into the cytosol. And similarly to glycogen metabolism, where its synthesis and breakdown were inversely regulated, glycolysis and gluconeogenesis are also inversely regulated. What activates one should inactivate the other. And that wraps up our time together today, folks. We talked through glycogen metabolism. We went through the 3 steps of both degradation and synthesis, and we learned that they are inversely regulated by small molecules and covalent modification through phosphorylation. And we saw that regulation can be directly connected to structural changes in the tertiary structure. Gluconeogenesis, we know now, is the reverse of glycolysis, and we've seen substrate cycles. All the rate determining steps are replaced, and regulation still occurs at those rate determining steps. Pyruvate to oxaloacetate to PEP involves carboxylation and decarboxylation to maintain the exergonic nature using those high energy molecules of ATP and GTP along the way. With that, I'll leave you with this cat meme. See you in class.